let's step back and maybe look at a bit of a romanticized version of mathematics.
Mm-hmm.
So I think you've said that early on in your life, math was more like a puzzle-solving activity when you were young. When did you first encounter a problem or proof where you realized math can have a kind of elegance and beauty to it?
That's a good question. When I came to graduate school in Princeton, so John Conway was there at the time. He passed away a few years ago. But I remember one of the very first research talks I went to was a talk by Conway on what he called extreme proof. So Conway just had this amazing way of thinking about all kinds of things in a way that you wouldn't normally think of. So he thought of proofs themselves as occupying some sort of space. So if you want to prove something, let's say that there's infinitely many primes. Okay, you have all different proofs, but you could rank them in different axes. Like some proofs are elegant, some proofs are long, some proofs are elementary, and so forth. And so there's this cloud. So the space of all proofs itself has some sort of shape. And so he was interested in extreme points of this shape, like out of all these proofs, what is the one that is the shortest at the expense of everything else, or the most elementary, or whatever. And so he gave some examples of well-known theorems, and then he would give what he thought was the extreme proof in these different aspects. And I just found that really eye-opening. That it's not just getting a proof for a result was interesting, but once you have that proof, trying to optimize it in various ways. That proof proofing itself had some craftsmanship to it. It's something for my writing style that like when you do your math assignments and as an undergraduate, your homework and so forth, you're sort of encouraged to just write down any proof that works. Okay, and then hand it in and get as long as it gets a tick mark, you move on. But if you want your results to actually be influential and be read by people, it can't just be correct. It should also be a pleasure to read. Motivated, be adaptable to generalize to other things. It's the same in many other disciplines, like coding. There's a lot of analogies between math and coding. I like analogies if you haven't noticed. Like you can code something, spaghetti code that works for a certain task, and it's quick and dirty and it works. But there's lots of good principles for writing code well, so that other people can use it, build upon it, and so on, and has fewer bugs and whatever. And there's similar things with mathematics. So.
Yeah, first of all, there's so many beautiful things there, and Conway is one of the great minds in mathematics ever and computer science. Just even considering the space of proofs, and saying, okay, what does this space look like, and what are the extremes? Like you mentioned, coding as an analogy is interesting because there's also this activity called code golf.
Oh yeah.
Which I also find beautiful and fun. Where people use different programming languages to try to write the shortest possible program that accomplishes a particular task.
Yeah.
And I believe there's even competitions on this.
Yeah.
And it's also a nice way to stress test not just the sort of the programs, or in this case, the proofs, but also the different languages. Maybe that's a different notation or whatever to use to accomplish a different task.
Yeah, you learn a lot. I mean, it may seem like a frivolous exercise, but it can generate all these insights, which if you didn't have this artificial objective to pursue, you might not see.
What to you is the most beautiful or elegant equation in mathematics? I mean, one of the things that people often look to in beauty is the simplicity. So if you look at E equals mc squared, so when a few concepts come together, that's why the Euler identity is often considered the most beautiful equation in mathematics. Do you find beauty in that one, in the Euler identity?
Yeah, well, as I said, I mean, what I find most appealing is connections between different things that you. So if you e to the pi I equals -1. So yeah, people uses all the fundamental constants. Okay, that's cute. But to me, so the exponential function was introduced by Euler to measure exponential growth. So compound interest or decay, anything which is continuously growing, continuously decreasing, growth and decay or dilation or contraction is modeled by the exponential function. Whereas pi comes around from circles and rotation. Right? If you want to rotate a needle, for example, 180 degrees, you need to rotate by pi radians. And I, complex numbers, represents the swapping between real and imaginary axes, so a 90-degree rotation, so a change in direction. So the exponential function represents growth and decay in the direction that you already are. When you stick an I in the exponential, it's instead of motion in the same direction as your current position, it's motion as right angles to your current position, so rotation. And then so e to the pi I equals -1 tells you that if you rotate for time pi, you end up at the other direction. So it unifies geometry through dilation and exponential growth, or dynamics, through this act of complexification, rotation by I. So it connects together all these fields of mathematics. Dynamics, geometry, and the complex numbers. They're all considered almost, they're all next door neighbors in mathematics because of this identity.
Do you think the thing you mentioned is cute, the collision of notations from these disparate fields is just a frivolous side effect, or do you think there is legitimate value in when the notation, our old friends come together and unite?
Well, it's confirmation that you have the right concepts. So when you first study anything, you have to measure things and give them names. And initially, sometimes because your model is, again, too far off from reality, you give the wrong things the best names, and you only find out later what's really important.
Physicists can do this sometimes. I mean, but it turns out okay.
So actually, with physics, so E equals mc squared. Okay, so one of the big things was the E. Right. So when Aristotle first came up with his laws of motion, and then Galileo and Newton and so forth, they saw the things they could measure. They could measure mass and acceleration and force and so forth. And so Newtonian mechanics, for example, F equals ma was the famous Newton's second law of motion. So those were the primary objects. So they gave them the central billing in the theory. It was only later, after people started analyzing these equations, that there always seemed to be these quantities that were conserved. So in particular, momentum and energy. And it's not obvious that things happen in energy. It's not something you can directly measure the same way you can measure mass and velocity and so forth. But over time, people realized that this was actually a really fundamental concept. Hamilton, eventually in the 19th century, reformulated Newton's laws of physics into what's called Hamiltonian mechanics, where the energy, which is now called the Hamiltonian, was the dominant object. Once you know how to measure the Hamiltonian of any system, you can describe completely the dynamics, like what happens to all the states. It really was a central actor, which was not obvious initially. And this helped, actually, this change of perspective really helped when quantum mechanics came along, because the early physicists who studied quantum mechanics, they had a lot of trouble trying to adapt their Newtonian thinking, because everything was a particle and so forth, to quantum mechanics, because now everything was a wave. It just looked really, really weird. Like you ask, what is the quantum version of F equals ma? And it's really, really hard to give an answer to that. But it turns out that the Hamiltonian, which was so secretly behind the scenes in classical mechanics, also is the key object in quantum mechanics. That there's also an object called a Hamiltonian. It's a different type of object. It's what's called an operator rather than a function. But again, once you specify it, you specify the entire dynamics. So there's something called Schrodinger's equation that tells you exactly how quantum systems evolve once you have the Hamiltonian. So side by side, they look completely different objects. So one involves particles, one involves waves, and so forth. But with this centrality, you could start actually transferring a lot of intuition and facts from classical mechanics to quantum mechanics. So, for example, in classical mechanics, there's this thing called Noether's theorem. Every time there's a symmetry in a physical system, there is a conservation law. So the laws of physics are translation invariant. Like if I move 10 steps to the left, I experience the same laws of physics as if I was here. And that corresponds to conservation momentum. If I turn around by some angle, again, I experience the same laws of physics. This corresponds to the conservation of angular momentum. If I wait for 10 minutes, I still have the same laws of physics. So there's time translation invariance. This corresponds to the law of conservation of energy. So there's this fundamental connection between symmetry and conservation. And that's also true in quantum mechanics, even though the equations are completely different. But because they're both coming from the Hamiltonian controls everything. Every time the Hamiltonian has a symmetry, the equations will have a conservation law. So it's once you have the right language, it actually makes things a lot cleaner. One of the problems why we can't unify quantum mechanics and general relativity yet we haven't figured out what the fundamental objects are. Like, for example, we have to give up the notion of space and time being these almost Euclidean type spaces, and it has to be, we kind of know that at very tiny scales, there's going to be quantum fluctuations. There's a space-time foam, and trying to use Cartesian coordinates x, y, z is going to be it's a non-starter. But we don't know what to replace it with. We don't actually have the mathematical concepts. The analog of the Hamiltonian that sort of organized everything.